I have chosen to do material A, which we are told is a 55 kilodalton block copolymer with about symmetric weight distribution between the blocks. Looking at a morphology diagram, we see that BCP morphology depends on volume fraction, which we will assume to be near 0.5 depending on the block densities. This is a one-component system with an ODT into different morphologies where the block copolymer blocks are segregated in different manners. In the 0.5 area, we see the lamellar morphology, the double gyroid or cubic bicontinuous morphology, and the perforated lamellae morphology. Looking at the scattering data, we see peaks indexed at multiples of square roots of integers. We would expect simple integer multiples for the lamellar and something close to integer multiples for the perforated lamellae in an unaligned sample. The double gyroid belongs to the IA3D space group, which is a subset of BCC. And the selection rule for BCC is that H plus K plus L is even. This means that the modulus would always be divisible by root 2, which has been removed from our data. So we can re-index our peaks by putting that root 2 back to get root 6, root 8, root 14, root 16, etc. And this is an exact agreement with the numerically predicted pattern for IA3D and the double gyroid morphology. Now that we've determined that our moduli should be multiplied by root 2, we can find the families of planes that the peaks correspond to. Our primary peak comes from 2, 1, 1. The next peak comes from 2, 2, 0. Then we have 3, 2, 1, etc. And it's worth noting that we do not see peaks from 1, 1, 0, 2, 0, 0, or 3, 1, 0. And the IA3D or gyroid space group is the only cubic space group in which we see all three of these peak absence, further confirming the identification. We can calculate now a lattice parameter is a equals 2 pi over q times the square root of the modulus. If we look at our primary peak, we see that we're at about 0.26. So we have 2 pi over 0.26 inverse nanometers times root 6, and that gives us about 59 nanometers. So now we're going to make a model of this structure. The basic unit of a gyroid looks something like this. It's these two trigonal pieces that are connected at 90-degree angles. And you can better see the threefold symmetry of the gyroid if you consider the unit to be something like this piece. And then if we take a few layers of those, we can build up one unit cell like they show in all of those fancy phase diagram pictures, which is basically made of stacks of these trigonal structures in alternating orientations. And so the unit cell looks something like that. Now that's hard to visualize and doesn't really look much like approximately a 50-50 by volume polymer. So if we take a model like this, coat it in a ton of caramel cubes, and then wrap it in tape, we get something that looks more realistic like this. This angle is sort of the angle that's normally seen in all those red and blue phase diagrams. And as you rotate around, you can see that this is just composed of a bunch of those trigonally trifold symmetric structures connected together along this one common axis along the cube diagonal. And so now we're going to take that, and we're going to attempt to go further and represent the other phase by embedding it all in a cube of Jello. So we've just put it in Jello, now it's sitting in the fridge, and we'll see what happens next. So our experiment was a success, and here we have a three-dimensional model of the double gyroid, which is based on the IA3D space group. Right now we're looking down from something like a 001 plane, and you can see the threefold symmetry very clearly if we look down this axis along the 111 direction. So here the black material is one block of polymer, while the Jello would be the other block. We've now removed the gyroid from the mold, and you can see it is much less pretty, but inside there is a double gyroid. And this is going to be the first ever tasting, probably in this planet, of double gyroid. Tastes like science.